Right. So our next speaker is Rachel Kuske from Georgia Tech, who will be speaking about computer-assisted global analysis of non-smooth impact dynamics inspired by energy harvesting. Yeah.
Okay, thank you very much. Thanks again for the invitation. So I'm going to talk again a little bit about non-smooth problems today. For some reason, this is a little bit cut off. Hopefully you can see my pointer this time. Yeah, good. So this is joint work with collaborators from Georgia State. Lanjing Bao, the graduate student there, has done a lot of this work, and her supervisor, Igor Belik, as well as Daniel Yurchenko, who's our collaborator in the UK. And I'll just start with a slide that I should have showed. I should have showed last time, which was thanking the funding and also quite a number of the people who've worked with over the years on various non-smooth things on the top line. But in particular, I'll talk today about some work we've been doing as part of an NSF EPSRC funded research group on energy harvesting and impact oscillators. Here it is. Just I'm going to start by telling you about the actually application. And I'm also going to. Yeah, the title maybe is not. This says global dynamics at the top, which was in my title. So, okay, so I'll tell you about the application, and then I'll tell you a little bit about what I'm not going to do. Hopefully that will set the stage a little bit for what I am going to do and why I'm going to talk about that. So essentially, this is a very simple model, but has been sort of advanced into a new model for energy harvesting. And it's, okay, so it's a simple setup. Basically, we have a cylinder that's being forced in some way, let's say, harmonic forcing. And there's a ball that can move freely inside this cylinder. And it can hit, either end of the cylinder. Now, the energy harvesting part, so this VIEH is vibro-impact energy harvesting, is that we actually have a dielectric polymer on either end of the cylinder, which can stretch when the ball impacts it. And because it has electrical properties, you have a change of capacitance with the stretching, and you can harvest energy. So essentially, you're converting mechanical energy into electrical energy. Now, you can think of where would you use such a thing? This is not like one of these micro things. This is actually, something that you can imagine putting on the side of a bridge or a building that has natural sort of vibrations, either from wind or traffic or whatever. And then you would basically charge, for example, sensors or other types of things on that structure without having to send somebody up to change the batteries, right? That's one example. Okay, and the nice thing about this setup is that the harvested voltage that you get actually goes quadratically with the relative impact velocity, that is the relative velocity between the ball and the cylinder. So that's actually quite a good harvesting proportion, compared to some other types of mechanisms. And we do have experiments going on in this with our UK collaborators. I'll say a little bit more about those later, but these are on very large scales of big platforms that can tilt and do all sorts of stuff, as well as smaller platforms that we've used more from the energy transfer point of view rather than energy harvesting. Oh, no, it's going. I don't know. It's frozen, I guess. Okay, so this is a very simple model. Essentially, you just have the cylinder being forced with harmonic oscillations. The ball doesn't move except if you have this tilted, then you have some gravity that will act on that. And really, the ball is moving just by the impacts, right? So you need to have it moving enough so that the ball actually goes back and forth. It's not, the ball itself is not being forced. So your basic dynamics are just drawn here. The blue line you can think of as the top and bottom of the cylinder as it oscillates. The ball is the red that goes back and forth, hitting the top and the bottom. In this particular setting, we're going to look at really the simplest possible case, instantaneous impacts, so that we're not modeling what's going on during the impact. The ball's mass we're taking as negligible compared to the mass of the cylinder. That allows us to actually put things in a relative coordinate system where we just look at the difference between, let's say, the center of the cylinder and the ball. And that we can then reduce down to this relative coordinate z, and in fact z dot. And that's actually useful because, as I mentioned, the relative impact velocity, which is z dot here, on impact, is basically giving us the energy. So that already, we can just feed that straight into our energy calculation. And the nice thing in this relative displacement, the ends of the capsule, of course, are not moving anymore. They're just straight, so that makes it easy. And in particular, in the phase plane, we just traverse our dynamics in a clockwise direction here, going from the left actually is the top, and the right is the bottom. And so essentially, we just have ODEs that take us from the top to the bottom. We have an impact. The impact velocity flips its sign. We have a negative sign here. It jumps down, right? And it also is reduced by some factor, R. R is the restitution coefficient of the impact, right? So if R was 1, we'd have perfectly elastic impacts. Typically, we don't have that because of the stretching and various other things, okay? So that's really the basic simple model. So it's essentially just, interspersing impacts with the ODEs in between the impacts. And I'm using the subscript here, K, to indicate the kth impact. So this is the impact velocity on the kth impact. Yeah, as I said before, it goes like the square of the, it's in a bigger calculation of this whole stretching and everything. But yeah. Okay, so, okay, this is not what I'm going to do today, but we can actually construct bifurcation sequences. Now, it would be nice if the ball was just nicely, regularly hitting top and bottom. That's actually your best energy production mode. Unfortunately, it doesn't always happen that way. We have lots of parameters in the problem. We actually have a non-dimensionalized parameter that kind of lumps them together. So we have mass, S is the length of the capsule, A and omega are basically the amplitude and frequency of the forcing. And so D is some non-dimensionalized length, and that we often use that as a bifurcation parameter. And so, okay, for certain values of D, here I've labeled things bottom and top, assuming I have a bit of a tilt. That's useful in breaking some of the symmetries. We have fewer solutions to track. So I can have a periodic solution. This is impact velocity watched after a long time to see if I settle into some periodic solution. So I can have a nice periodic solution that hits once on the bottom, once on the top. We call that 1, 1. And then, but then I can have other types of solutions that hit, for example, twice on the bottom and once on the top. And in the phase plane, okay, these look like nice loops when it's just 1, 1, but when it's 2, 1, okay, I cross once, then I can come back and hit the other side. And in between, we have something called a grazing bifurcation, which is where, instead of moving, let's say, from the bottom to the top, the loop comes around, just touches on one impact. Basically, that's the same as the capsule moving and the ball just touching and then continuing. So it really is actually grazing. And those tend to give rise to this, transferring from this 1, 1 behavior to 2, 1. As you can see over here, we can also have more complicated things. We can have 3, 1, we can have 2, 2, we can have all different combinations. And we can also have, period doubling, as we see here. We can have chaotic solutions that are some combinations. Okay, so lots of things can happen. And maybe just to zoom in, yeah, just to say a little bit more, what this grazing is. Here we can see basically the transition from just a regular hitting bottom, then top, then bottom. That's what's over here, to this grazing where we just touch. And then the 2, 1, where we're actually hitting once on the bottom, actually twice on the bottom, then again on the bottom, and then on the top. Okay, so that's just giving you really what it looks like. Okay, so we can track all these sorts of solutions, of course, because really we only have 4 possibilities in terms of what sequence can we have, right? So we could go from the bottom to the top or vice versa, but we can also hit again on the bottom. So any of these types of behaviors I've been telling you about, we can think of in terms of a map, that we're not tracking necessarily our state space and everything over time. We're just tracking our state space in terms of what happens from impact to impact. Okay, and so our state space is really going to be just our impact velocity at impact j, and that time has to be one of the variables of state space because we have a non-autonomous system, right? It's being forced with this harmonic oscillation. Often, actually, through this whole talk, instead of time, I'll talk about impact phase, which is essentially the difference between where we're hitting and let's say the minimum of our oscillation. So there's going to be some phase shift there that matters when we're actually finding our impact solution and our energy. Okay, but anyway, without those as the state variables, then I just have maps that go between those state variables, whether I'm going from bottom to top or top to bottom. And I can write any sequence of these as a combinations of these maps, which I've just called here P, all right, all different types. Okay, so we can piece those together and we can have all sorts of maps. Okay, so that's kind of our basic building blocks, but I'm not exactly going to use these. But okay, maybe before I get into that, let me just say what's different about this problem is for the energy harvesting, we really want this thing to be hitting on both sides all the time, right? And that generates all sorts of other solutions that you have to track. In contrast with a lot of other, let's say, more mathematical studies of impacting systems like the bouncing ball, or there's often these single wall type impacts where you think about a pendulum that swings and then hits a wall and then changes its behavior. Or as I mentioned last time, we had these clearance contact dampers for damping seismic activity where you have an oscillator sitting that can hit a wall in the floor and actually damp seismic activity. So those are all kind of single-sided impact behaviors. And often in those sort of problems, you're looking for kind of onset from not impacting to impacting. Or in the bouncing ball, a lot of it's been studied in terms of what happens so the ball kind of settles. That turns out to be, I mean, it's sort of related, but it's quite different from this case where we really, our basic state is hitting both sides all the time. And so it's just, there's more stuff to keep track of is basically what I'm trying to say. Now, so what does this mean for energy? Okay, as I said, we want to have the ball hitting both sides all the time, okay? And as I told you, we have different sorts of solutions. Let's just concentrate on this 1-1 where we're alternating bottom and top, the 2-1 where we might be hitting more than once on one side. Okay, so we can calculate the energy from now. There's a relatively simple formula. And okay, it just looks like this on the bottom. But what is this really telling us? And let's zoom in this little purple region where we have a transition from this 1-1 to 2-1. Okay, so the blue and the green here on the right are just the energy we collect from the bottom and the top. They're not the same because we've tilted the capsule a little bit. The average is the red here, okay? And this is just when we're going 1-1, okay? So we average that. This is the average per impact. Okay, but as soon as we go to 2-1, that red line, the average per impact drops. Because even though we've added an extra impact, it's a small velocity impact. It's very close here to z dot, our impact velocity, close to 0. And so that gives us per impact a lower energy per impact. Is that good? Is that bad? Well, you could say, well, but per period, these solutions are sort of per forcing period. Actually, the pink stars here actually correspond to energy per time interval, let's say. That actually goes up because we've added an extra impact. Now, the question here is, there's wear and tear involved with every impact. Do you want more impacts where some of them are kind of useless, right? So we're constantly having these arguments about which energy are we really interested in. But it does show you that, yeah, you will get a different type of energy depending on what sort of solution you're going to get, okay? And, okay, so the other question here is these are local solutions, right? This is a bifurcation diagram. We did local stability analysis for particular solutions that we were able to construct out of compositions of these maps. in general, we actually want to know, are there other solutions? Because in general, there's all sorts of stuff going on that can push us out of one solution to another. Do we have other solutions? And so we're interested in global dynamics. And maybe to quote Paul Glendinning, who's kind of an expert in maps and non-smooth things at a non-smooth conference, saying, the question is what can't happen? Because as soon as you start putting in non-smooth things, different sorts of events, you can get like almost anything. So that is kind of an issue with these systems, especially as I'll mention at the end, there's other sources of uncertainty and multi-stability that can make a difference. Okay, here's one example of why we might care about this. So this is a slightly different parameter regime. I've changed it a little bit so we don't have all the chaotic stuff going on to make it a little simpler. But this is kind of an example of why you would care about global dynamics. So what I've shown here is, again, the impact velocity versus this parameter d. And on the upper graph, I'm actually lowering d and following the branches. And I have this grazing bifurcation. So I'm going from 1-1 to 2-1 type solutions. Okay. The circles are the deterministic case. The green is stochastics. And so we see that this 2-1 is actually coming in for a higher value of d. And if I look at this the other way around, we also see that as we increase d, the 2-1 kind of survives, at least in a continuation sort of way, longer for d, even in the deterministic case. So there's bistability between these two types of solutions, plus the fact that some type of noisiness in the problem can actually sustain one of them much longer than we might expect, right? So this kind of tells us we have, weak attraction to certain types of solutions in certain parameter regimes. And so we would be interested in when is noise actually going to change the solution we expect to see. So I'll come back to this example sort of more towards the end after we first kind of develop some approaches. Okay, so just to kind of fill in a little bit of the gaps here. So I'm kind of looking at almost the very simplest case you can think of what's called an impact pair, where something is being forced and then there's this ball moving back and forth inside. These show up in more complicated versions in a number of different application areas, as I've shown here. One to mention, for example, in this energy transfer case, for example, this seismic energy transfer. In that case, we would actually take the mass not to be negligible, right? If you want energy transfer, the mass should not be negligible. And then we cannot go into this relative framework, and we're actually in a higher dimensional problem, like from the start. There are various bifurcation analyses for these. There's an interesting application where biomedical devices actually also can use this impact pair model. I won't go into that, but just to give you a sense, there's quite a bit out there that uses this impact pair type model. There's of course plenty of bifurcation and stability approaches for non-smooth systems, discontinuity maps, saltation matrices. There's lots of computational methods. Looking at computational Lyapunov exponents, things like this. But sort of a common theme is that whenever we look at these non-smooth maps, first of all, they're typically kind of ugly. And second of all, they're quite sensitive to parameter changes. And so, recognizing that, we'd like to get more of this global picture. And there are, methods for, and the Nordmark map is actually a very commonly derived map for these single-sided impact systems as well. So that's just to kind of say what's out there. But we haven't found that particularly useful to go beyond these local analyses. There's very little, as far as I know, in terms of approaching these sort of hybrid, non-autonomous ODE plus non-smooth systems for global analyses. There is some work on the bouncing ball, but that's studying the stability for the non-bouncing state, like how much does the ball damp out? That's great for the ball. It doesn't really help us for the energy harvesting, because then we're just not harvesting energy. There's a lot of course, computational methods like computing basins of attraction and path integration, cell mapping. Again, very expensive methods that, as soon as you start getting into higher dimensions, are pretty difficult. And in fact, basins of attraction don't really help us very much. So just to remind you, like, what do we really want to get out of this global view? And we'd like to know, where are we going to get the best energy? What sorts of regimes are going to give us different sorts of energy? We'd like to have efficient regimes. And in fact, we'll even see that some chaotic behavior is not necessarily detrimental from an energy point of view. But we also have this problem of multi-stability that can jump up in many different ways. So that's kind of the things we have in the back of our head. So with that in mind, I'm going to start with essentially looking at a very, very simple problem as a toy problem to kind of develop an approach or a viewpoint for these problems. And it's actually looking at the fact that, I can construct this bifurcation picture for the impact velocity. But in fact, in terms of a solution that gives me the energy I want, actually any of these solutions in the green box are good, right? Because essentially the energy for these are more or less the same. Even though this is chaotic, it's still, it's not getting close to these small impact kind of useless behaviors. And so, in fact, I don't really care if I resolve the bifurcation picture here, but I would like to know where my impact velocity is going to live, okay, in terms of, is it going to be away from zero, if it's going to be close? And so the stuff in the red box is where I start to have transitions, so those are the cases I'm going to worry about. Okay, so I'm going to actually just start by trying to develop a method to look at the green box, not to resolve the actual behavior, but at least to get a sense of where does my impact velocity live. And, again, I've just shown kind of a blow up of the experiment here. So this is basically a transparent tube. Hopefully you can see the ball here. It moves back and forth. But for example, a lot of the data we have now shows, what variability do we have in the restitution coefficients? How does that actually change our bifurcation behavior or not? And we actually see, we can get kind of, quite random behavior in that and still be sustaining, these sorts of solutions. And there's, other friction, other sorts of parameters that we can take into account. Okay, so that's the basic idea. That's going to be our warm-up problem. So what sort of hurdles do we have in looking for that? So if we're just asking, from our maps, so these are essentially the maps we have going from impact to impact that we got from the original ODEs and the impact conditions. Trying to write down, at least we were not successful trying to write down anything in terms of Lyapunov function or anything like that, because they're non-autonomous. We're actually interested in multiple impacts. It's just a mess. So if somebody has a great idea, that would be fine, but we haven't figured that out. So in just thinking in terms of this very simple problem, when we thought about it, we're really, actually we don't really care if we have both the top and the bottom impact. In some sense, if we know the bottom, then we know the top, we can get that. And so we're just going to try to say, do we know where the impact velocity actually lives without reconstruct, but we're not going to reconstruct this bifurcation figure. And then also our impact phase is part of our state space. So we're going to track that as well. So we're going to say, can we somehow figure out where our impact velocity and phase live in order to tell us what sort of energy we can get without reconstructing this? But what we really want is we want all the transients, right? Because we want to make sure we're not going to end up in some other type of behavior. Okay, so that's the basic idea behind here. So as I said, we're not going to construct. Oops. Okay. We're not going to construct the solutions. Instead, we're going to look at what kind of building blocks can just tell us about transient and attracting behavior. And we're going to even just focus on what happens kind of on the one side of hitting the bottom. And eventually we'll get to an auxiliary map for global dynamics, but that'll be a few steps away. And then, as I mentioned, we want this to have, it would be nice if those building blocks had some relationship to energy, right? The things we like. But we don't have to do that, but it'd be nice if they do. Okay, and then the other piece is, with this idea of, identifying attracting or repelling or transient sorts of behavior, the return map type idea that we would have would also be nice if we can somehow use that. Okay, so that's the basic idea. Okay, so actually, I mean, in some sense, this slide is kind of like half the talk. Like, if you can find the right set of return maps, then hopefully that helps you to sort out different sorts of behavior. And again, we're in a very simple case, but the idea is to identify something that we could generalize to more complicated cases. And so we're just going to talk in terms of return maps that take us from hitting on the bottom to then hitting again on the bottom, but all sorts of stuff could happen in between. But we're going to restrict it to just a few things happening in between. So one thing that could happen in between is nothing. So we just come back to the bottom. And the other example is we could go from the bottom to the top and then come back. Okay, so and a lot of our sequences can be constructed from just combinations of those two, if you like, words, right? So made up of these symbols from going from bottom to top to bottom. We could also have other sequences where we hit the bottom, we hit twice on the top, or we hit 3 times on the top. For at least to start with, we're not going to take those into account because basically for physical reasons, if you have a bit of a tilt, hitting twice on the top is actually really unlikely unless you start with a huge impact velocity, which is immediately damped out by the restitution coefficient. So we could keep track of them, but they kind of wash out in the analysis pretty quickly. So what we first did is just say, let's take our state space. So this is phase versus impact velocity. I start with an initial value, and I just follow it once. So I just say, okay, what happens until I get back to the bottom again? And in certain parameter regions, I hit the bottom again without hitting the top. That's the black regions here. And in the pink region, I hit the top in between. There's a blue region here. It's actually part of the pink, and we'll see why that's special in a little bit. But the point here is we're not doing basins of attraction. We're just taking one step in terms of starting at the bottom and coming back with very few definitions, very few options of what can happen in between. This kind of data, yeah, they get pretty much this. This is what they can observe. Yeah. Okay. Now we've had lots of questions that people have said, isn't this just a Poincaré map? And I'm not calling it a Poincaré map, partly because later on, we actually will be interested in, as I mentioned, these 2-1 cases where we hit twice on the bottom and then top and then come back. Because in some sense, then we're measuring 2 returns to the bottom, right? And actually, even though you could think of getting one of these by combining the 2 other words, we'll see it's useful to actually separate out this case where you can hit both a top and a bottom before returning to the bottom, if you like. And so we'll get to that in the noisy case later. But anyway, so we have this division of our state space, and for what happens in between returning to the bottom. And then you could ask, okay, that just tells me what's going to happen. Of course, you want to know what's the value at the return, right? So that's going to be my z dot at k+1, or my psi, my phase at k+1. And so this is what the maps look like if I graph them versus the initial conditions. They're ugly, they're piecewise messy. So, the question could ask, have we improved the situation in any way, or we just made it worse? Okay, so this is essentially what we've done. We just divided into 2 different maps, one where we can hit the top in between and one where we can hit the bottom. So the question is, can we somehow translate this into attracting regimes, which is what we're kind of interested in, and transient regimes? And another point that we followed, although it may be a bit of a distraction, but we tried to see if we could get some sort of closed form representation of the dynamics, meaning can we at least approximate some parts of these surfaces where it might be useful to have a closed form expression for stability, but it's not necessary. We can do this computationally. Okay, so now I'm going to appeal to, the fact that we're thinking about return maps, right? So can we project this into the phase plane and think about, for example, as you would with a return map, what happens near the diagonal, which might give you some sense of, am I returning there, returning to this state again or not, okay? And so what we do is essentially project these surfaces. So again, the pink as we hit the top, black as we don't, onto the phase planes for velocity and phase separately, and ask, are there parts of these surfaces that are essentially intersecting the diagonal for the same parameter values, which would suggest, for example, some kind of fixed point, okay? And we can identify different regions like that. I've sort of highlighted them in blue and yellow. Then the question is, are they potentially attracting? Are they potentially transient? That, of course, depends a lot on how do they cross the diagonal and whether the way they cross suggests that we're like shooting off to some other value, or are we somehow staying close to that value so that we would return to it. Okay, so now you could say there could be other more complex behavior, and that's a fair enough point. But for now, this is going to work to some extent. So this basically doing this projection or comparison of these ugly surfaces to the phase space actually helps us to eliminate quite a lot of what's going on in this particular problem. Okay, so yeah, maybe what I've shown down here is back in the state space region. So this blue, okay, which is, that's what I actually had, that blue region in the pink in the previous slide, is actually going to be essentially our potentially attracting region. And we're actually getting it from this stage, but we still have to kind of worry about what are some of these other regions doing. Okay, so so we've identified some return maps. We've started to look at them in taking the maps, looking at them in the phase plane to start identifying what's attracting and what's not, right? And this is just to remind you that, I'm not actually worrying about whether it's periodic or a fixed point or anything. I'm just asking what's returning in some way into some region. Okay, so we're going to try to work towards getting an auxiliary map that's going to tell us about this attraction and how big is the attraction. We're going to have to work a little bit harder for that to just kind of eliminate what's transient and what's not. Okay, and this is just to remind you, we are interested in all sorts of different behaviors. Okay, so this is the advertisement in the middle of the talk for hopefully this crowd, because I'm not really in the field of the workshop this week, but a lot of the discussion has made me think about this phase plane, and we know we have a lot of directionality from the system, and so I basically sort of wrote down this state space and the regions that we've divided using these different sorts of behaviors, and added the arrows that we kind of know what's going on, right? And we can get a lot of this from the shape of these surfaces that I've shown you here, okay? And again, this is a relatively simple case. As you can sort of guess here, things they can roam around, but they eventually end up in this blue region. But if I change the parameters a little bit, we can actually have things jumping back and forth between the pink and the black and the blue, and then we can have other sorts of behaviors going on. So I think this would be a fun model to sort of put into one of these connection matrices or whatever maps that you'd like to look at. And I think it'd be great for these sort of non-smooth problems where otherwise there's not a lot out there. Okay, so that's the advertisement. Hopefully that's woken you up a little bit. Okay, so to continue on, this may be a little bit of a red herring, but as I said, we also wanted to write down some things explicitly. So we actually did take some of these surfaces and approximate them with some polynomials. But in order to do that, I mean, these things can be very sharply curved. That's horrible for approximating. So in fact, that's why this identification of potentially attracting regions is useful, because those are the ones we really want to focus, a reasonable approximation on. And the others we can be a little rougher about. So in fact, this blue region, which I've kind of hinted already, is the potentially attracting region. We can identify a rough bound on that by comparing things in the phase plane. Then we can also look at some of these other surfaces. So this is in this corner region, which I've called R3 here. We can look at those surfaces, we can fit them, but in fact, we kind of, we don't throw them out, but we put them in the transient bag, let's say, relatively quickly, partly because the shape of the surface for phase is so sharply peaked that we know we pretty much move on to a different phase relatively quickly after just a very short number of iterations. Okay, so that kind of gives you the flavor of, we do have to kind of work through these surfaces. And there's a whole algorithm we can put together for that, that essentially says, identify your subdivision based on your words or your sequences that you're interested in. Try to see if you can approximate some of these. Can you actually capture the behavior or not? Often you can't because the surfaces are just too ugly, in which case you can subdivide further. Okay, so in this problem, we actually subdivided into, even though we really just have 2 regions, we just subdivided into 5 in order to get a better idea of, being really able to classify things as transient and not. Yeah, so it's a great, so this is written down with the idea that this could all be automated. I cannot say it was all automated, but a lot of it we get from doing this projection of the surfaces into the phase plane. And also because the surfaces have to simultaneously cross, let's say, the diagonal in both the impact phase and velocity, a lot of times they just don't. And so that already helps you to move away from those. And then in certain cases where the surfaces is just too steep, then we tend to divide those up just to be able to do a better approximation. So some of that we can measure, if you like, but I would not say it's super accurate. But in this case, because so much of the space is transient, we could kind of get away with it.
Okay, so you're kind of classifying the regions with a certain behavior with the classification problem. You have data.
Mm-hmm.
You want to know about
Yeah, absolutely. I totally agree. Yeah. Yeah, we could do this much better, I'm sure, different ways. Yeah. No, I think there could be lots of ways to do this. Okay, so then the kind of the last piece in terms of the global dynamics and identifying what's really our attracting region. So we've kind of identified a lot of regions as transient. So we're going to focus on this blue region where we actually have what we expect are the absorbing dynamics. It's a very rough approximation to that region, and we'd like to do better, right? Because we're trying to figure out where does our impact velocity live. And so in order to do that, we developed an auxiliary map, which basically just says, take the maps over this region in both the impact velocity and the impact phase, and look at their max and min and try to see if that can tell us something about where our dynamics would be bounded. The other nice thing about this is if for example, I take the max and the min of the velocity over all values of the phase, I actually turn this into the bounds on a one-dimensional map. So I have 2 one-dimensional maps, which I can run simultaneously, but then hopefully that tells me about a little bit more about the region. Okay, and then we do sort of what we call a worst case scenario cobwebbing, which is a lot like cobwebbing, but we essentially take sort of the max on the upper curve, look at its image, take the min on the lower curve, look at its image, and then ask, okay, if we do that again, but again, taking the worst case scenario, either the max or the image that we just got and repeat that, do we actually somehow get a smaller region, right? So we start with this rough approximation with this whole box. We use this worst case scenario and we end up with a smaller box. Okay, so already we're doing better, but then we could ask, well, we started out with a really bad approximation. Now we have a better one. Now, what if we start with that one and repeat the process? Okay. Now this doesn't work very well if we would just take the entire map, because it's a totally crazy shape, right? So the fact that we've kind of reduced where we're looking, our curves are nice enough that we can, for example, if they're just strictly monotonic, this is relatively straightforward. They can be a little bit fluctuating, but if the curves are not too bad, this worst case scenario works pretty well. And that's kind of the payoff we've had in reducing where we're actually looking. Okay, so this is just showing as I update my worst case scenario region, apply this cobwebbing again, and then I repeat that. This is actually, in this particular case, we've done this about 10 times. And so this is a zoom each time. So down here, I have a small box that I'm getting to, but it's really the little black dot in the, like 8 steps above. So, and this is the case where we actually have a fixed point. So I've taken my parameter value where we do have a fixed point. So we never really get a fixed point, right? Because we're always doing max and min, but at least the box is getting pretty small, right? And now you can say, well, what happens if we do this? Oh, sorry. And then, yeah, we get basically a size of this box in terms of V. Sorry, I should have mentioned this before. V is really the approximation to the impact velocity, which was Z dot before. I've just turned it into approximate variables. And phi is again our phase for psi. So we get a box on V and a box on psi, or box on impact velocity, which is what we want. And then we can ask what happens if we look at this, for example, in these other parameter values. In the period doubling case, okay, the box shrinks, but it stops shrinking at some point. It'll plateau, right? And the same with the chaotic attractor. And it just so happens, which it should hopefully, that the size of these boxes is essentially the size of the range that we have in the period doubling or in the chaotic regimes, right? So it is giving us some kind of reasonable approximation of where our system is living without actually resolving the bifurcation. Okay, so we've essentially gotten this identification of what are the attracting regions and the size of those regions, which we can then translate back into the impact velocity, which gets translated into energy. Okay, we've done this in this very simple case, so still simple, but this auxiliary map has been a very useful way of doing kind of a iteration on these maps to take what can be quite a crude approximation and reduce things down. Now, we always get cycles, as I mentioned, but the cycles can be quite small or large depending on that behavior. We do get some explicit expressions in this case, partly because we have once we've reduced things, we can get a pretty good polynomial approximation. But again, that's not necessary. We can do this without having those as well. Okay, now our focus was on global attraction. But we did actually, just to kind of check, we actually constructed the full composite map by doing various approximations also in the transient regions. Here I've just, shown that you get the period doubling and the chaotic. I mean, there's some horrible, like trying to put a 4-dimensional phase space into something and track the map. Okay, so that's just what all these curves are, but we can reproduce those. We actually use a very crude approximation in the transient region. So if we actually look in state space, we don't really resolve all the transient behavior, but it's partly because we were less worried about that and more wanting to resolve what's in the attracting region. So there could be better things done in those regions. Okay, so this was basically this very simple case where we're just trying to reproduce essentially this top bottom behavior, but where we could be chaotic, could be fixed point without having to resolve that. So now if we go to the bistability and the sort of robustness to noise case, now I'm not going to do the full analysis here, But my point here is that we can get a lot of information just by identifying the right words and dividing up the state space, okay? Particularly if we're interested in where does noise actually play the role. Okay, so all I'm really going to show you here is dividing up the state space and a little bit of this projection. So now we are going to divide up our state space based on 3 different words, just going from the bottom to the bottom, hitting twice on the bottom and the top and coming back, or the same thing as going bottom, top, then hitting twice in the bottom, or just the alternating case, right? And so not really surprising that we divide our state space. The 2 bottom, top, bottom actually is a combination of these 2. So it kind of lives in between the 2. And I've drawn here the stable state for this particular value of my bifurcation parameter lives in this alternating case. And now I'm going to change the bifurcation parameter and see what happens. So as I change this bifurcation parameter, the region, this red region where these hitting twice on the bottom and top, bottom again, starts to expand and, kind of shrinks the alternating case. And we get this little piece, hopefully you can see it here, this green piece coming down. That's still bottom, top, bottom, but kind of like Baja California. It's like sticking out into the Pacific Ocean. And it's getting surrounded by the 2-1 where we hit twice on the bottom. And that continues in that range until we completely lose it, right? So this already tells you a lot. And this is, again, just running for 1 return. So it's super fast because I'm not running this in any length of time. I'm just asking what happens after 1 return. I can already see where the noise sensitivity is going to come in. But that's, of course, if I happen to know that the a potentially attracting state is, somewhere near these boundaries. And that we can get fairly, and let me just say that this gives us a lot more information than, for example, a basin of attraction, because a basin of attraction just, basically tells us about initial conditions and running a long time, but it just gives us all sorts of little pieces that we can't really do much with. But so we can actually identify, is the competition really with this little Baja Peninsula and the rest by doing a projection of these maps, again, into the phase space for the impact velocity and the impact phase, and asking where we have intersections, which can tell us basically, do we have potential attractors in certain regions or not? These are just some examples where, because of the way things intersect, we think we have a fixed point for bottom, top, bottom, but we think we don't for the hitting twice on the bottom, because we would actually need 2 intersections for that to give us a potential attractor. And then we can change D, and then things change where we actually lose the attractor in one type of region and we gain one in the other type of behavior. And again, that's just coming basically from this projection. Now, the other nice piece about this is if we look at actually the shape of the maps, it tells us a lot about why is the noise biasing us towards hitting twice on the bottom rather than, the other way around. And we can see that from looking at, what's the shape of these maps. This is in phase near the attractor, which is over here. And as we change our parameter, we still get this sort of big hill here in phase. We start to lose the attractor, but in fact, trying to have noise that pushes us, let's say, to larger values of phase, the noise never can push us there because we have this big hill. So we're always going to be pushed to smaller phase. And then you can go back to the maps and see that, sure enough, smaller phase always corresponds to 2-1 behavior and not 1-1. Okay, it's hard to see here, but zooming in, you see that. And that's essentially what's going on in these bifurcations. So the noise is actually more often than not pushing you towards this other type of behavior where you have 2-1. Okay, so that's without really doing any analysis, just running the maps, looking at their behavior and potential attracting behavior, which tends to focus on, very actually small sort of parameter regimes. Okay, so hopefully it's giving you a little flavor of what's going on. This is just kind of getting started as identifying potential ways to look at stability in these non-smooth systems from a global point of view. Things get worse if we, put in more realistic stuff. So these are some of our former postdocs who've worked on these more, the more realistic stuff, like adding friction. Friction is definitely there. Friction actually can help you sometimes because it eliminates a lot of the chaotic behavior. But what it does add, friction adds sticking and sliding. So that means you're adding another type of non-smoothness, which means you're adding more to your maps, the different maps in different regions you can be in. You can look at compliant impacts, actually modeling the impact with the dielectric polymers. And that actually is useful because we know that a lot is going on in that impact that affects the behavior. So that's, yet another equations you have to keep track of. And in the energy transfer case where the mass is non-negligible, as I said, you can't go into this reduced framework. So you're already in like 4 or 5 dimensions just with a simple model like that. And then, of course, to really make this useful, we'd like to have these energy harvesters in some sort of network where we're actually multiplying the effect. So these are all different configurations. And we can even have, let's say, multiple cavities within one unit, right? And that's yet another sort of type of coupling that you have. So that already cranks up the dimension, cranks up the possibilities that you would have. And you'd prefer not to construct the full bifurcations for those things. There's also an interesting consideration we have in terms of energy billiards, where instead of just going back and forth from one end to the other, having a table where you would have polymers all around. Okay, that already adds another dimension to the problem. It was actually motivated by our experiments because the ball is already kind of rattling a bit in this tube. So we're like, well, why not actually use the sides, right? As well as just the end. So that's a whole other bunch of behaviors you can get there as well. So let me just put the advertisement up again. So there's a lot to do here, especially when we start going into these higher dimensions with networks and so on. So I hope I've piqued your curiosity there. Maybe we have a chance to try out some of the cool tools that we've been talking about this week on these problems. I'm sure lots of engineers would be happy with you if you could do that. And then let me just thank the funding and my collaborators once again. Thanks very much.
I'll ask a simple question. So the R coefficient, the restoration,
Restitution,
must be proof factor. I mean, so where the energy comes from? The energy must come from somehow it must affect the movement of the ball. There's mechanical energy of the ball.
Right. Yeah. So we're harvesting natural vibrations. Let's say. So if it's like a bridge, it's like okay. Yeah.
Lose some of the extra energy.
Yeah, and that's the R. That's the R. Yeah. Yeah. That's the R. Yeah. And the R, as you said, we're taking R constant, but really the R should depend on the velocity, the impact velocity. We do have data on that, so we kind of have a sense of how that behaves. So that would add yet another, sort of variability in the map. Yeah. Yeah. No, if R is 1, no, you still have harvesting, but because it still stretches. But it's unrealistic in the sense that you're always going to lose some energy in that impact. I mean, it would be great if R was 1. Can we go back to Baja California? Here we go.
So I guess I'm missing something about what the base of attraction constellation, right? I mean, if that really was kind of the base of attraction experience, then you're one step. You're saying that what would be said there is that the one step is just what happened now and in the future.
Yeah. So actually, this is flipped. Sorry, I didn't have one that was flipped the other way. So it should be flipped. So like this curve here should really be like this curve. So it kind of mimics what's going on, but the problem is with the typical basin of attraction computations is, yeah, it says what's going on initially, but then, okay, if I start here, maybe I go here, okay. But I mean, it tells you what may happen over a long period of time, but it's not necessarily looking at this problem where you have randomness all the time. This is just random initial coefficient. And so this is telling you, well, maybe on the edges, there might be some sensitivity. You have no idea why, right? And so it's just telling you like, okay, and
That's too detailed, given that there's randomness.
well, I mean, it's a detail that's not really physically of interest, I guess.